we're going to be reviewing coordinate proofs, arc length and sector area, circles, parallelogram proofs and properties, using trig to solve word problems, equations of circles and volume. This podcast was just going to include the first three topics, and let's start with coordinate proofs. All right, so here are just some general formulas that we use in coordinate proofs. For coordinate proofs, we're proving something about a geometric figure on a coordinate plane. So we'll use the distance formula, the midpoint formula, slope, and slope formula. Okay, so here's just kind of a review of those. We use the distance formula to show that segments are congruent, the midpoint formula to show that line segments are bisected, that midpoints are the same, and then the slope formula to find parallel and perpendicular lines. All right, so in your notes, we have this proof here, and we're given some information, and we're looking to prove that our triangle DEF here, is an isosceles triangle. So all the information that you see here is also on your notes, and all the statements are there. We're going to add the reasons. Right, so the first thing that we see in our proof, we see that the coordinates of the vertices of triangle DEF. Always we start off with our given information. So the reason that we can list those coordinates there, 2, 5, F is at 2, 5, and D is at 1, 1, and E is at 5, 2, is because that's given information. We're given that triangle to work with. So you can just add that to your notes. All right, so what we're looking to do is prove our triangle is isosceles. If we want to prove the triangle is isosceles, we have to show that we have two sides congruent. And what would we use to show the two sides are congruent? Well, we'd have to use the distance formula. So you can see here that in step 2, we've used the distance formula to justify the length of segment DE. So segment DE is the square root of 17 units long, and we know that because we use the distance formula. So formulas are always one of your possible reasons when you work with coordinate proofs. And we know the length of DF is the square root of 17 because we use the distance formula to find that as well. So you'll find with these coordinate proofs, a lot of times it's formulas that are your justifications. PS is, oops, I have a little typo there. So on your notes, I had a different triangle in here, and then I decided to switch it, and because I liked this one, it was at a slant. The other one was kind of boring. We need to change that. It should say DE is congruent to DF. There is no PS or PR. All right, so DE, why do we know that DE is congruent to DF? Well, if they're both equal to the square root of 17, they're both equal to one another. So we can either use substitution. So if DE is equal to the square root of 17, and DF is equal to the square root of 17, we can replace the square root of 17 with the DF. Or, since they're both equal to the same thing, they're equal to one another. So you have two choices for justification here. You can either use substitution, and then you're just replacing the square root of 17 with DF, or you can use the transitive property because they're both equal to the same thing. And so now that we've said that side DE is congruent to side DF here, so this side's congruent to this. Once we've said that, we can say this is an isosceles triangle, and we can say the triangle DEF is isosceles. That's the definition of isosceles triangles. It has two congruent sides. That's what it means to be an isosceles triangle. So we have now finished this proof. We've now proven that this is an isosceles triangle. Okay. So you're going to find the proofs in this section are all kind of the same format. We're proving different things, but we are going to use our formulas from algebra to prove some things about our geometric figures. All right, so here, a little bit different proof. And so there we can see we got our figure, and we've got some information here. And the first thing that we see in our proof, coordinates of vertices of triangle POS and triangle ROS. So there's two triangles there. I don't know if you notice it, but add that line and you can see the two triangles. And we know those, we have these triangles because we're given that information. We're given the coordinates of the triangles. That's part of the picture there. All right, so now let's look at part 2 there. So we have PO is equal to 3, RO is equal to 3, SP is equal to 5, RS is equal to 5. And below that we have some other information that goes with it. And you can see, how do we know that PO is equal to 3? Well, we use the distance formula. And we found the difference in the x coordinates and the difference in the y coordinates. And the square root of 9 is the same thing as 3. And this is the same thing as 3. And square root of 25 is 5. Okay? So the reason that we can make those statements, that we can find the lengths of all of those segments, is that we used the distance formula. So that would be the reason in our proof. Simply the distance formula tells us the measure of the segments there. All right, so we can, all we've got right now are the lengths of our sides, nothing more. Step 3 here, we have SO is congruent to SO. Why is something congruent to itself? That is the reflexive property. Now that we know that, we can say that triangle PSO is congruent to triangle RSO. I think if we write some of the information down on our picture, it'll make it a little clear which of our triangle congruence postulates we're using. So this was 5, SR was 5, and then RS, PO is 3, and RO is 3. So these are 3, and this is 3. Well, you can see that PO is congruent to RO. Right? I'll just kind of put that over here. So PO is congruent to RO. PS is congruent to RS. Those segments have the same measure. And then SO is congruent to itself. We know that 3 sides in one triangle are congruent to 3 sides in another triangle. That would be side, 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 triangle congruence postulate. Because the triangles are congruent, all of the corresponding parts of those triangles are congruent. So we know that angle PSO is congruent to angle RSO because the triangles are congruent. You cannot say congruent, you cannot use CPC-TC, congruent parts of congruent triangles are congruent, until you prove the triangles are congruent. There has to be a triangle congruence postulate first. Okay? So you can't use this until you state that the triangles are congruent. Okay? So this always follows stating that 2 triangles are congruent. All right, so now that we know those angles are congruent, we can say that SO here, ray SO, bisects angle PSR. And the reason that we can say that is because an angle bisector divides an angle into 2 congruent angles. So if those 2 angles are congruent, ray SO has to be an angle bisector. Okay, and this proof is now complete. Right, so we're using, because our figures are on the coordinate plane, we get to use some of our formulas, and we also use some of the postulates and properties that we've learned earlier to complete proofs. All right, so we're given that quadrilateral, we're given the quadrilateral with coordinates L at -2, 3, M at 4, 3, N at 2, -2, and O at -4, -2. And we want to prove that LMNO is a parallelogram. Of course, we always start off with our given information. We need a place to start with. Once we have our given information, then we can work from there. Right, so the next thing that we've shown here in our proof is the length of OL. Okay, so OL is the square root of 29 and MN is the square root of 29. And how do we know that that's the length? Because we use the distance formula. You can see it right there, that the distance formula was used to find the lengths of those two segments. The slope of OL is 5/2, and the slope of MN is 5/2. Well, how do we know it's 5/2? We use the slope formula. And that's our justification for step 3. OL is congruent to MN, it's just substitution, or you can even use the transitive property. They're both equal. You can either say, okay, I can just substitute the square root of 29 with MN. Since MN also equals the square root of 29, I can just replace it. Or you can say they're both equal to the same thing. They're equal to one another. Okay, so either the substitution property or transitive property shows that these two segments are equal to each other. OL is parallel to MN. Well, if two lines have the same slope, then they're parallel. So lines with the same slope are always parallel. That's our justification on why those two lines are parallel. So now that we have shown that OL is congruent to MN and that OL is parallel to MN, we can see now which reason we're using to show that this is a parallelogram. Always make sure that when you solve something out and you show something's congruent, or you're given some information about something being congruent or parallel, make sure you mark it on the figure so you can see. So now we're not just looking at, that, oh, we got slope, maybe it's both sides parallel. Or, oh, we got, two sides congruent, maybe it's both sides congruent. It's neither one of those. We know that quadrilateral LMNO is a parallelogram because we have a quadrilateral with one pair of sides that are both parallel and congruent. If we proved one side was parallel and another side was congruent, that wouldn't prove it was a parallelogram. It's because one pair of sides are both parallel and congruent, that we know that this is a parallelogram. And our proof here is complete. Okay? So this is one of the ways that we could prove a figure is a parallelogram. I put all 5 ways in your notes that I gave you. All right, so now let's look at this proof. So this proof's also in your notes. So now we got this one, and we're going to do one more proof. All right, so we're given quadrilateral with the coordinates A at 1, 2, M at 2, 5, N at 5, 7, and O at 4, 4. And we always start with our given information. Okay, and then from there, we can use any of our formulas to show that quadrilateral LMNO is a parallelogram. And one of those formulas we can use is we can find the slope, because we know some things about the slopes of parallelograms. And so our reason for number 2, this is the slope formula. So we can use the slope formula to find the slope of sides of a figure on a coordinate plane. AB is parallel to DC, BC is parallel to AD. How do we know that those lines are parallel? Because they have the same slope. Parallel lines have the same slope. So you see the reasons here, they aren't tricky to remember, really. They're things that you know. And it justifies why those lines have to be parallel. If you have the same slope, you're parallel. So we can see from our figure that these two are parallel. We have that in our proof. And these two sides are parallel. So the reason that the quadrilateral here, AB, AM, oh, it looks like I've got the right points, but the wrong letters. I must not remember to change the letters when I retype things. So this really should be A, B, C, D. Now that's correct. So why don't you correct your figure? A, B, C, D. Right coordinates, just the wrong values there. So sorry, a little cut and paste, and I forgot to change the letters. Everything else there is right, just those letters are wrong. I didn't even notice it. Just got two into the proof, I guess. So we can see that quadrilateral ABCD is a parallelogram because it has two sets of parallel sides. Okay. So make those little corrections there and fill in the rest of the information on your notes. And so, this is going to help you remember why you can say that two lines are parallel, or why can you say what the slope of two lines are, or the length of two lines. Okay? We're using our formulas, and we're using our triangle congruence postulates and facts about parallelograms and parallel lines. Got one more proof for you. And I think this one's a little bit trickier. You can see it takes up 6 steps here. And I forgot to put the letters on here. So on your notes, the first thing we're going to do is we're going to write down the points. So the points are listed on the notes. They're listed above here, but they're not put on the graph. So let's put those points on the graph so that we can see what we're talking about. So A here is at 5, 6. So right here is A. B is at 3, 2. C is at 6, 2. D is at 1, negative 2. E is at negative 1, negative 6. Looks like my line's a little short there. And F is at 2, negative 6. So right there is F. All right, so put those on your figure there. We want to prove that angle ABC is congruent to angle DEF. Okay? So we can't take out a protractor and measure it. We have to use only formulas from coordinate geometry to be able to prove this. And one thing we can do is we can use our slope to help find some things out about the angles, because we know if we have parallel lines, we know certain angles are congruent. If we have perpendicular lines, we know that the angles are right angles. So we know some things just by finding the slopes of lines. So the very first thing that we've done here is we found the slope of BC and EF. And so why can we say the slope of BC and EF are 0? Because we use the slope formula. So easy. You figure this out. You probably already written in slope formula because you knew I was going to say that. And so now that we've said that those two lines have the same slope, we can say that lines BC and EF are parallel, and we know they're parallel because parallel lines have the same slope. A, B, D, and E all lie on the same line. Now that one might be a little bit tricky. Okay? So let's take a look and see if we can figure out what line they lie on. Okay? So if we continued that line ED here, so if you notice here, the line here has a slope of 2, doesn't it? And you can just, if you take a look between any 2 points, the line goes up 2 to the right 1. So we have a slope of 2. So we can keep counting that out. We can go up 2 to the right 1, up 2 to the right 1. So the orientation's okay, it's just a little slow. So if you notice that these we could connect those, and they're all part of the same line. So what line is that they lie on? Well, we got to think back to writing equations in slope-intercept form. So let's write the equation of, let's call that line EA. Okay. So we're going to use slope-intercept form, y equals mx plus b. all we need to do is identify the slope of our line, which we just did. We were counting it. Our slope is positive 2. And the y-intercept. And the y-intercept, we can see it right from our graph there. Our y-intercept is at 4. So you see, all of these points lie on the same line. The line that they lie on is y equals 2x plus 4. How can we be sure, though, that those points lie on that line? Well, we could check by plugging the points back in and seeing if we get a true statement. Okay? So I'm gonna just do that right over here. So let's check and see if the A, B, D, and E all lie on that line there. Okay? So our equation is y equals 2x plus 4. So we'll plug in, we'll test A first. So then we would have 6 equals 2 times 5 plus 4. Wait, did I? Oh, excuse me, minus 4, minus 4. Sorry, our y-intercept is negative 4. I'm looking at the graph, forgetting that it's up pretty high, and when I'm looking at 4, it's not positive 4, that's negative 4. I knew something looked a little wrong there. That's a negative 4. We're below the x-axis there. Positive 4, I have to put my head way back to see. So I'm sorry, that equation should be 2x minus 4. And so let's just fix our equation, and now let's try and plug it in, and I think that will look much better. Well, now that's a true statement. So as we have 6 equals 10 minus 4, and that is definitely a true statement. So you can see that A is on the line, and we can do the same thing with B. So 2 equals 2 times 3 minus 4. 2 equals 6 minus 4. That's a true statement. And we can check out D. Negative 2 equals 2 times 1 minus 4. So negative 2 equals 2 minus 4. That's a true statement. And we're kind of running out of space here. Let's check out the last point, E. And so we have negative 6 equals 2 times negative 1 minus 4. Negative 6 equals negative 2 minus 4. And that's a true statement as well. So because we got a true statement when we plugged all of the equations into the equation for that line, we can say that the points satisfy. And when we say satisfy, it means they make a true statement. They satisfy the equation y equals 2x minus 4. So because we get a true statement for all 4 of those points when we plug it into the equation, we know that they lie on the same line. Okay, so we have a line, we've got 2 parallel lines, and a line that intersects those parallel lines. Well, what do we call it when we have a line that intersects parallel lines? Remember back from working with parallel lines, this is a transversal. So this y equals 2x minus 4 is actually a transversal that intersects our 2 parallel lines, EF and BC. So now that we know these points are all on that line, we know that our lines EF and BC are parallel. And so now we have parallel lines intersected by a transversal. If we have parallel lines intersected by a transversal, we know the corresponding angles are congruent. So ABC and DEF are corresponding angles, same position on a parallel line, same side of the transversal, and therefore those have to be congruent. That's the definition of corresponding angles. So corresponding angles formed by parallel lines cut by a transversal are going to be congruent. And so now we've proven, because they're corresponding angles, and they're created by those parallel lines. We know that ABC is, oh, excuse me, I shouldn't say and, I should say is congruent. All my little typos. ABC is congruent to angle DEF, and that is the corresponding angles formed by parallel lines. So in the step above, we just said that we should show that they were corresponding angles. Corresponding angles, they don't have to be congruent. They're only going to be congruent if the lines are parallel. Because our lines are parallel is the reason that those corresponding angles are congruent. And now we've proven those angles are congruent. This was definitely a tricky proof. I can definitely see some parts that you wouldn't necessarily have figured out what to do and not realize that, hey, if you continued, they all form the same line there. Okay? So I hope this one made sense. You definitely will see a problem like this and should be able to solve proofs that involve parallel lines. Okay? All right, so I hope you were okay with our coordinate proofs here and this all made sense to you. I'm going to briefly go over circles and arc length and sector area. I definitely think that this was the topic I wanted to spend a little more time with because this is definitely a trickier topic, those coordinate proofs. Okay. So the arc length and sector area, I have these notes are in your notes, and they just remind you of the steps. Okay. So just remember that the formula for arc length is the fraction of this is the central angle over 360. That gives us the fraction of the circle. And then you're just going to multiply that by the circumference of the circle. And of course, the circumference of a circle is 2 pi r. Oops, I was just trying to underline that and not have that go across my 2 pi r. So all these steps are in your notes, and so it goes through just finding the length of AB here. I think this is a pretty straightforward problem, and you can just review those steps in your notes. If there's any part you can't see, you can just pause the tape and go through it with your notes. Okay? And then if you have questions in class, you ask me. All right. Let's look at sector area. So here we have the formula for sector area. It's the fraction of the circle, which is going to be your central angle over 360. Times area of the circle, and the area of a circle is just pi r squared. Okay, so very similar problem. The only thing difference is instead of 2 pi r, we have pi r squared. We have area instead of circumference. And then of course we're going to reduce it to lowest terms. Okay? And again, if there's any part you want to go over, it's in your notes. And if you need to pause it, you want to look it over, on the screen, go right ahead. If you have questions, ask me in class. I do want to do 2 area problems and 2 that are maybe a little bit trickier because they look a little different. Right, so we want to find the area of the missing piece. And maybe this is a pizza, and the blue is the part that's left, and the blank part here with nothing over here is what somebody ate up, right? So we want to know how much they ate, okay? All right, so first of all, we want to make sure we identify the correct central angle. Okay? So if you just look at the 235 and say, that's your central angle, you've made a mistake because that's the angle for the part that's left. For the missing part, okay, it's going to be 360 minus the part that remains, 235. So that means our central angle is 125 degrees. Right? 360 minus 235 will give us 125. And then we need to know our radius. You must use radius when working with sector area. With arc length, you can use diameter. Just remember that if you're going to use diameter, the circumference is pi diameter, or 2 pi r. But with area, you've got to use the radius. So we're given that the diameter is 20. So if the diameter is 20, the radius is just half that. Okay, so make sure you identify your central angle and your radius accurately, and you should have no trouble with these. So now let's find the area. So the area, I'll just put A for area, is our central angle over 360 times pi r squared. And then we just substitute in. So our central angle is 125 over 360. I should really make that 25 look a little nicer. Looks a little bit like an 8. Times pi times 10 squared. So we need to square the 10 first. So we have 125 over 360 times 100 pi. And you can put that over 1 to help, keep everything in the right place. And then we can reduce. We can cancel out the 0. Remember, you always reduce numerator to denominator. 10 and 36 are both even numbers, so we can divide by 2. So that would be 5, and that would be 18. And that's it, because 125 is not divisible by 3, 2, 6, 9, or 18. So that's as much as we can reduce. So now we just multiply the numerator and multiply the stuff in the denominator. So 125 times 5 would be 625 pi over 18. And this was inches squared. And that's our area here. Okay? So it shouldn't be, hopefully that's not too difficult for you. Just remember, make sure you know what you're finding the area of. In this case, it's the missing part. I'm going to do one last problem, and I'm going to end this podcast, and this one is just going to be just a real quick one. We're finding the area of the shaded sector. Make sure if you're given the diameter that you find the radius. So if the diameter is 10, that means our radius is 5. Okay. And now it's just central angle over 360 times pi r squared will give us our area. And so the central angle is right here. It's 100 degrees. If the arc is 100, so is the central angle. Those are exactly the same. So this is also 100. So we have 100 over 360 times pi times 5 squared. Writing's taking a little while to show up. We'll square. So we have 100 over 360 times 25 pi. We can reduce. So for the last problem, hope you probably remember that not only is it divisible by 10, it's divisible by 2. So it's divisible by 20. 100 divided by 20 would be 5. 360 divided by 20 would be 18. And that is it on this problem. So our area is 125 pi over 18. And that is centimeters squared this time. And that's all there is to finding the arc lengths. The last thing in this portion of the podcast, so we found arc length, sector area. We've done our coordinate proofs. I'm going to leave this for you to review. You see the no for benchmarks. These are some facts about circles that you must know by heart. Okay? And that includes the inscribed angles. You have to know the relationship to the intercepted arcs. The inscribed angle is half the arc. Okay. Just put that right there for you. Add this to your notes if you like. Inscribed angle equals half the arc. Okay, that's one you should know. Also, you need to know that, and it's also right over here too. If you have two inscribed angles and they have the same intercepted arc, then the angles have to be congruent. So here, if you notice that angle A is right here, and there's its arc, you just follow it right, the angle right out to the circle where the two sides of the angle intersect the circle as its arc. And here's angle B, and just follow it out. There's its arc. And you see they have the same arc. They have to be congruent to one another. And if we have a semicircle, an angle inscribed in a semicircle, it's always going to be a right angle. And I think I have that picture on the next slide. So that one is right here. So I'll kind of go over those really quickly with you. So here, angle is half the arc. Angle B is going to be half the measure of arc AC. And in this case, if the arc is 88, the angle is half of that. Okay, so make sure you know those. You don't need to write these down. I can put those in your notes for you so that you would remember them. And if an angle, here we have an angle, it's inscribed in a semicircle. So here notice that the endpoints of the angle are on the diameter. This is always going to be a right angle, and it will always be 90 degrees. Okay? Which makes it real easy to find the other one, right? Because we can just find the measure of the arcs that it goes with. So here, if this arc is 74, this whole semicircle is 180, means that this arc here is 106 degrees. Angle B is an inscribed angle. Its vertex is on the circle. It's going to be half of 106. And here we have another demonstration. If two angles have the same intercepted arc, two inscribed angles, same intercepted arc, they're going to be congruent to one another. Okay? So all of those are in your notes. Review those, and I will come back in the next podcast to review some more with you. The last two, almost forgot, the last couple concepts are also in your notes. Make sure you know the names of all these segments. Memorize them, okay? And make sure you can name them. And one fact to know about tangents, and we went over this in class, and we solved some problems. If we have two tangents and they intersect in a point, those tangent segments are congruent. Okay? Remember, this was the hat theorem, and everyone laughed because it looks like a clown. That's this theorem here. So PA is congruent to PB. They are the same measure because they're tangent. We can see we have a right angle, so they meet the radius at a right angle, and they intersect in a point, so they have to be congruent. Okay? So that's the end of this podcast. Review these notes, and then when you're done reviewing, you can watch the next podcast. All right, see you later. Bye.